Okay, we have a short problem here regarding heat and enthalpy. So aluminum metal can be recycled from scrap metal by melting the metal to evaporate impurities. So we've got some scrap aluminum and we can melt it down so we keep all the aluminum and the impurities evaporate away. Calculate the amount of heat needed to purify 1 mole of aluminum originally at 298 K by melting it. The melting point is 933 Kelvin. The molar heat capacity is this figure, and the heat of fusion is this figure. So sometimes these can be a little bit daunting, but let's just envision what we're talking about here. Let's say we have some aluminum. Let's make that a different color, actually. Let's do this. So let's say we have some aluminum here, and it is sitting at, it's 1 mole, and it's sitting at 298 K, right? So what are we going to do? First, we have to heat it. We have to heat it up to, we have to heat it up to 933 K, right? Because we have to get the metal to its melting point. And then we have to melt it. So, and then it'll be a liquid, right? So those are the two steps involved, right? We have to get the solid aluminum to its heated up to its melting point, and then we have to melt it. And we have two different figures that will help us do that. So if we're going to get from 298K to 933K, we're going to need the molar heat capacity. So this is 24 joules per mole K. And they made it nice and easy for us. It's exactly a mole. So let's just multiply by a mole just to get rid of the units. And then we're going to multiply by 635K. Whoops. 635K. That's the difference between 933 and 298. So 300 to 600, 300 to 900 is 600 plus 33 plus another 2, if you want to do that mental math there. And so that's going to get rid of moles. That's going to get rid of Kelvin. And we're going to end up with 15,000, exactly 15,000 joules, which is 15 kilojoules, right? So if we have 15 kilojoules, now, so that is the heat required to get the aluminum to the melting point, and now we have to add to that. So the heat of fusion, that's the energy required to melt it. It's 10.7 kilojoules per mole, and we have 1 mole. So it's just 10.7. So 15 kilojoules plus 10.7 kilojoules. We're gonna obey sig figs here just because we're being thorough. That's gonna be about 26 kilojoules. Okay, so 26 kilojoules. That is the amount of heat needed to get this process to go. Heat up the aluminum and melt the aluminum. So, yeah, so that's the answer to part A. Now, B, the equation for the overall process of extracting aluminum from this aluminum oxide ore. So now we have this naturally occurring ore. That's shown here, which requires less energy, recycling existing aluminum or extracting aluminum from aluminum oxide. So how do we do this? Well, we've got a delta H value here. We have a delta H value associated. Now we have a chemical reaction. This was a physical process, heating and melting. This is now a chemical reaction, so we have a delta H associated with that reaction. We have an enthalpy value. This is the amount of energy required to get this to go. And we're trying to, this figure is for 1 mole of aluminum. So let's get the same figure for here for 1 mole of aluminum. Here, this is the amount of energy required to get 2 moles of aluminum, right? We have 2 moles of aluminum there. So we just cut it in half. That's going to be 837.5 kilojoules per mole of aluminum. right? And so if we're going to compare 837.5 kilojoules to 26 kilojoules, obviously recycling is going to be the one that requires way less energy, right? We can see this is like 30 times less energy to recycle it than to extract it from an ore. So this was actually pretty straightforward, right? All we did was use a heat capacity and heat of fusion to calculate an amount of heat required to undergo a physical process. We compared it to the delta H for a chemical process and saw that one was much, much smaller than the other. So that's a little bit about heat and enthalpy.